this is, okay, so this is an experiment as well, in that it seems to me that if you try and look at things this way up, it's easier for you to do some things that you're surprised about, but it's an experiment to see if it actually works in an intelligible way. But I hope you'll find it preferable. Okay, so the premise that I'm starting from is you've done a lot of things about quantum mechanics. And indeed, you have a fantastic 24 lecture series on quantum mechanics, which is absolutely fantastic, and it's monolithic and it's wonderful. And what that does then is it teaches you how quantum mechanics works. And basically, above everything else, what the course does is it gets you to a point where you start having some understanding in your guts as to what works. And it's a weird subject, and you need lecture courses of that length before you begin to sort of some sort of feel as to what's happening. But I think that having done that, so this is predicated on the fact you've already done a decent quantum mechanics course. You couldn't possibly look at the world this way around if you hadn't. But once you've seen it from that point of view, the problem you have when you go that route, you have to go that route because you have to start with what you know, which is classical mechanics. And you have to then say, well, how would we end up believing in quantum mechanics if we started off with classical mechanics? Do you see? And so you think about operators and things like this. And the whole thing is done completely arbitrarily. At each stage you're saying, well, let's invent an operator which does this. Well, let's type a Schrödinger equation out of thin air. And that's inevitable because you're forced into that way of looking at it because you haven't yet learned the subject. But once you have learned the subject, I think you can start at the other end and say, okay, let's just forget we know anything about classical mechanics and relativistic mechanics. Forget we know anything about anything in quantum mechanics except the basic observations, and let's see where that gets us. Do you see? Because then you can see how the basic observations feed through into the quantum mechanics one has. This is what I'd like to try and show you. Okay? And the remarkable thing is you start with some very simple assumptions, and it doesn't take many sides before you've derived what energy is, why it's conserved, and why relativistic and classical mechanics are the way they are. And the whole thing follows just from some relatively simple observations about how the waves behave. And you get to a point where you understand why E equals mc squared, and you understand what mass is, and you understand why mass is energy, etc. So this is the A. Okay. Now I reckon now, but it is predicated on the fact that you always have those components already. So it's sort of okay. So that's what we're going to try and do. Now basic observations, it starts off with the observation that light is quantized, and that you have quantum mechanical behaviour, but that you have particles behave as waves. Originally, light proof was possible to spot, and indeed people have done this with beams of atoms. You make a beam of atoms, have a shadow, and you find that the atoms end up in the middle of the shadow. It's just quite a nice demo. You can do a diffraction of atoms. This is something sitting in a lab, which diffracts atoms, and so you can measure the intensities, function, angle, get nice sharp diffraction patterns, blah, blah, blah. So this is sort of proof. You can take quite large objects and diffract. So this is diffraction of buckyballs. One slit's collimate, two to do young slits, with and without. With no two slits, one young slits, you've got diffraction. And you can, he showed this in your course, they're massive molecules which diffract. Now at this point, you see, if you stop, this takes a bit of swallowing. Because you see, I think most of us could sort of accept that a photon can be a waving particle. Yes. But to swallow the fact that the whole extended molecule, its centre of mass motion can be described as a wave, a single wave. And it diffracts according to its centre of mass motion, despite the fact it's a really complicated object. That means your car has a wavelength and will diffract. It starts getting slightly bizarre, but that's the observation. And indeed, on this case, of a molecule like this, its wavelength is 20 angstrom. Yet the whole thing is 330 angstroms big. So the centre of mass wavelength of this object is, I can't do the maths, but it's 300 times smaller or something. 600 times smaller. Yes. So that's what we observe. Now you quickly realise, and you've done the quantum mechanics course, that the point is that particles are not dots, particles are smudges, and the problem is that when the chemist said stuff is made of particles, we imagined dots, we imagined billiard balls. That's just wrong. They're not smudges. And so if you're worried about an atom going through two slits, you're only worried about that because you think an atom's a dot, the end, they're smudges. So they have no problem going through two slits. Okay? Now the wave packet really does go through both of them. If you take an example of this, so you have this nutty observation that you've got two slits, and the wave comes along, the photon comes in, and you get a diffraction here, which proves you only get that pattern if it goes through both. If you block out one, you change the diffraction pattern. It really goes through both. So it really is there and there at the same time. You can do it in time as well, and this is the schematic of the machine which sits in our lab. Basically, you have a surface in vacuum that you want to investigate. You create a beam of helium-3, and helium-3 has a nuclear spin, and so it has a little magnetic moment. So you can polarize it on its nuclear spin, so you have them all nicely polarized. You then put it into a magnet, and you see if you have a little bar magnet with north and south perpendicular to the solenoid, if it's aligned with the solenoid, so you've got the solenoid is like this, north-south, but your thing is polarized like that, north-south. So when it goes in, its energy depends on the orientation of that with respect to that. This is a spin-half particle, so it can only be up or down, which means when it gets to here, it has to answer, are you like that or like that? So it says, well, I'm a 50-50 mixture of them, and the wave packet splits. There's one bit goes ahead, which is sucked in, the other goes behind. That one hits the surface first. You then recombine them, and you measure the polarization. And the point is, my point is that this one particle is half of it is here, and half of it is further down the line. You've split the wave packet. And you can see this is the case because the one that's ahead scatters in a different way to the one at the back. And when you put them back together, the polarizations change, and you can use this to measure the motion of the cells. It really works. You can take a wave packet, pull it apart, do things to it, put it back together again, and it works. So the basic observation of quantum mechanics is that you can take away not just wave packets, but you can separate them. You can do things separately to the components, and then you can put them back together again. And this works. Microscopic interferometers is exactly that. Okay. Now, so that's the wave packet. You've seen things like that before. As if you take, this is a plot of wave vector against, and that's what wave looks like. You have just one wave vector. You put two wave vectors in, you get beat frequency. If you put more in, of course, you still get beat frequency. They're rather hideous. If you allow for a nice Gaussian distribution of amplitude, you get nice Gaussian distributions on the wave packet. But then, if you reduce the spacing of this increases, and if you reduce the spacing again, you just get one of them. So if you have a continuous range of K, you end up with a wave packet. So that's how you make a wave packet. And you can see that there is a trade-off, that if you have a wide spread in Ks, they go out of phase very quickly with each other, so the wave packet is small. If you have narrow spread in K, it takes a long time before you go out of phase, and it's big, hence Heisenberg's uncertainty relationship. Okay. So this is the basic sort of phenomena that you've got in quantum mechanics. And the nature of the wave packet, its coherence length, how long it is, depends on the spread in light, for which it's made, and its width depends on the source and things like that. So they're topics you do in quantum. Okay, so we've got the fact that they're waves, and we've already hit the fact that you can decompose them and add them up. And that's decomposing and adding up turns out to be a very key property. So let's think about measurement. What is a measurement then? Now, given we're starting off with waves, what is a measurement? Now, a measurement is when you split the wave up into components. At heart, that is what a measurement is. The classic case is if you take a diffraction grating and you send a photon in, that this incoming wave thing, so you have an incoming wave packet which is made of a spread of components, yes? Right? And when it goes to diffraction grating, those components are spread out. So red ends in that direction, and blue ends in that direction, etc. And so you then say, right, if I put a slit here, if I get a photon going through here, it was red. If I get a photon going through there, it was blue, right? And so you measure the energy of your photon by splitting it up into components. But that does not mean the original thing was either red or blue, right? Now, at that stage, you're not quite sure whether you believe this. We'll come to a minute. You say, oh yeah, it was always red. It was red beforehand. Honest. It has to be red beforehand. Okay. We'll see in a minute that you can show cases where it was uncertain it wasn't. Now, another classic case is that's a position. That you have a wavefront comes in. And to measure a position, what you do is you put it into a slit. Now, you could consider this wave function if you plot it, now this is a plot, right? That's psi as against distance. You can consider this to be split up as a pile of columns, right? So in this case, the wave packet is decomposed into 4 components. In this case, you consider it decomposed into a set of columns, of which only one goes through. Yes. So you select that part of the wave. Yes. And if a detector here detects a photon or something, then you conclude that the particle was here. That's how you measure position. So what happens, you see, is that the world is quantum mechanical. It's made of waves. We trundle along, and we start trying to measure things. And we make measurements. But what happens is, the things we find we can measure, we're hitting on ways of selecting different bits of the waves. That's what's actually happening. We don't realise that's what we're doing, but actually, every measurement we make, because it's a wave, boils down to different ways of selecting bits of it. Okay? And the Stern-Gerlach experiment is a classic case. You know, they said you split it into 2 waves. One goes up, one goes down. Up is spin up, down is spin down. It's all, any measure, think about it, any measurement you make, as a fundamental level, it's not just a fundamental level, things have got so far away that quite what's happening is obfuscated. If you think a bit harder, you can see this is actually what's going on. That any measurement boils down to selecting a bit of the wave. Now, you're supposed to say, aha, this is just statistics, that actually the wave was at that place. All right, yes? It was red. So if you had your slits, you'd say, well, that's fine. The fact it went through here means it really did go through there. Fine. That means if you block that up, it shouldn't make any difference, should it? True, but it does. Right? So it's not just statistics, it went through there, or could go through there. It must have gone through both. Now, a good example of this, you can show this on the bench quite nicely in the school's demo. And what you do is you measure polarization. And first of all, you tell them that light is quantized, so it arrives 1 photon at a time. And then you say, okay, so we're signed up to the fact it's quantized and arrives 1 photon at a time. You say, fine. Well, now what you do is you put it through a polarizer, so all the photons going through the polarizer are lined up like that. Yes? You say, fine. Now I'll put a polarizer like this. How many of them go through? And you ask them to say, none. You say, that's fine. How many go through if I put the polarizer like this? And they say, all of them. That's fine. Right? How many will go through if you put it at 45 degrees? Right? Now they of course say none. But you know what the truth is that what happens is this thing can be regarded as a mixture of electric field like that, 2 components. And what the polarizer does is it splits into components. And if you have Brewster angle, right, the Brewster angle of light, one component of the polarization goes through and the other is reflected. So the polarizer is splitting your components. Now in this case, because it's just gone through a polarizer, you know it was polarized in that direction. It is polarized that direction. So it's not that when it arrived at this polarizer, it was actually already polarized like that, because it's just gone through a vertical polarizer, which means it's polarized up. Do you see? Yeah? So it really is the case that the thing is not just statistics. When the photon arrives, it is perfectly, it behaves as though it really was a white light photon, made of all these components. And when you make a measurement, it answers randomly. And of course you can wind them up, as I was talking about this, and saying, well, what's the worst thing you could possibly do if you answer randomly, and of course that's what it does. Okay. And you demonstrate it, and you get this, the curve which just proves it. So you get this quantum mechanics on the bench. That is a quantum mechanical phenomenon, and is a demonstration of this collapse of the wave. It's very strange. Okay. So, now, what's then, so what have we got? We've got stuff in about waves, we've got the fact that measurement corresponds to selecting a particular part of the wave, and we've got the fact you can decompose something into different components. Now, this does not always work with everything. Not everything in the world will decompose into components. So let's find something to illustrate this, and it doesn't work with rotation. So supposing we take this box and we rotate it about a vertical axis 90 degrees, then rotate it about an axis towards you like that, it ends up pointing that way. Now let's rotate it 90 degrees about that axis, and about the vertical axis it ends up there. Yes? So the order in which you do the operation matters in rotation. That means you cannot describe rotation in terms of a vector, and it is meaningless to decompose a 3D rotation into components. Because if you split them into components, some of that and some of that, when you add them back up together, you don't get the same answer, do you see? Yes. So this is not a formal conclusion that you can split something into components and add them back up again and it works, do you see? But the observation is, see my spin echo experiment, that that's exactly what happens with these waves. So that then becomes a cardinal and fundamental observation. Now, you then have these observations are encapsulated in the postulates of quantum mechanics. Now, when you do the postulates of quantum mechanics, you think, this is mad. These things are just plucked out of thin air. Where's the derivation? Where's the reason why? Where do these things come from? Well, what you're missing about the fact is, it is not a derived result. It is a clear and simple way of summarizing the experimental results. Do you see? So the postulates of quantum mechanics are a summary of experimental results. What it says is, we observe that the way the world behaves is like this. And this behavior described in this model, that is a summary of our observation of the world, you see. That's why they're not derived. You see, they're just simply a summary of what we observe. It is nothing more than, they are nothing more than an empirical statement of summary of what we observe, which is why there's no attempt or need or reason to derive it. It's just a statement of a summary of what we observe. Okay, now the postulates you know, there's a state function, then we have observables, and we have eigenfunctionality. All of a sudden we're talking about Hermitian operators and stuff. And then we have the Schrodinger equation. Okay, so why are we all of a sudden talking about Hermitian operators? Where might that come from? But before that, why might it be that the probability of a measurement goes as the square of the amplitude? Let's just think about this a bit. So we have a wave, or a wave, and that can be split up into components of different frequencies. Now they add linearly, that's the whole point of the observation, so you can write your wave as a sum of coefficients times component waves. Now a wave has amplitude and phase, and so if you want to specify it, this thing has to specify two numbers, you need amplitude and phase, which is why you use complex numbers, yes? Because you have to do two numbers to specify a wave. But if you're going to say, I want to know how much of this wave and how much of that wave, we want one number, don't we? Not two. So you can't get it from the amplitude, you've got two numbers, at least not directly. You've got to do something to the amplitude which gets rid of one of the numbers. Plus also you want something which manifestly carves up the amplitude in an intelligent way. Now again, the vector amplitudes don't do this, because you see, you could have that equaling some of that and some of that, or it could also equal some of that and some of that. So just taking the length of the amplitude is not much use, you see. But if you have a orthogonal basis set, if you have functions which are orthogonal to each other, then they behave like vectors. In a vector diagram, you can have some of this and some of that. As you know, under those circumstances, you add them to get this, and the amount of this compared to the amount of that and that is given by Pythagoras' theorem. Yeah? Now these things manifestly are scalars, and they add, don't they? They just add nicely. You can divide that to some of that, some of that, and some of that. You see? And they're all positive numbers. So it's not a complete surprise that if you wish, so we go into the world, we get the waves, we carve them up into different things, and we work out that you can associate numbers with these, which give the probability of finding. We want some number which is associated with these things, which is going to sensibly tell us how much of the different bits we've got. So it's not a complete surprise that we hit on the square of the amplitude. Can you see? Because the amplitude itself doesn't have the wrong behaviour, but that does have the right behaviour. So it's not surprising that when we do this, we end up with the notion, we discover that if you want to assign probability, it matches on to this fundamental behaviour of the waves. That just comes from the fact they're linear waves, you see. So we stumble across this. So you can sort of understand where that might come from. Now, why are we all considering Hermitian operators? Well, let's think about how you would work out an average value thing, given the story so far. How would you work out the average value? So, for example, you want to know the average wavelength, or the average k vector of a photon. Well, the first thing you do is you take your photon and you split it up into a sum of pure waves of different colours. Right? Now, each of those has a certain wave vector. Right? Now, what you want is the average value of the wave vector. So what you want is the sum of that multiplied by that squared. You see, that's the probability of the wave. So if you want the average value, it's going to come out something like that. Okay, so if you want the average value when you make a measurement, you make a measurement many, many times. It answers different colours. You take the average according, and that's what we end up with. Well, fine. Now, supposing, however, your wave function was delivered to you in a different basis set. So, for example, in 2D, supposing x and y is the basis set you want, but someone says, okay, fine, but I've got a different basis set. I'm going to use these ones. And so you've got the coefficients of these ones. We'll call that capital C1, capital C2. You know, there's in order to get those coefficients, you multiply by a transformation matrix, yes? And then you want to do this stuff, because that's giving you the coefficients in the ones you want. So you do this stuff, right? And then you want to transform back. Then you have to multiply by these coefficients the other way around. So in order to get this gives you one set of coefficients, to get the other, then you have to have the transformation matrix here, and there's things like that. Now that means you're looking for a way of doing this stuff in terms of matrix, yes? And it turns out, of course, that if you want to write this thing in terms of matrix, you put the k's along the diagonal, and you put one vector there and the other vector there. Okay? So you can see that the desire to work out an average value, the fact it's linear and behaves like vectors, the fact that you could have a different set of coefficients leads you to say, okay, we will represent our measurement in terms of coefficients, matrix coefficients. And it's a respectable way, it handles the way it transforms to different coordinates. It's obviously a good way of doing it. Now, once you've done that, you realise these have to be Hermitian matrices. All right? Now, can you see that you've got a Hermitian matrix? That's what the properties are. So you can describe, if you have a wave function, you can write it as the sum of some coefficients times a basis set. You know, some are red, some are green, some are blue. And if you then, to operate on this thing, you've got some sort of matrix which does the trick. And so you can represent the effect of this matrix on this because it just puts in, it multiplies by your measurement coefficient. As you know, these turned out to be eigenvalues of the matrix. Now, that is a way of representing an operation of something. And so that, if you think about the maths, you could describe in terms of a function which operated on this, and you end up with Hermitian functions. So what drives you towards thinking about Hermitian functions is that if you think about how you work out a probability, the maths has the right form, and that is going to deliver the goods. Now, these Hermitian, there's inevitably, because you've gone down that route, and because it works, it's also true that if you take a Hermitian operator, so for example, if you take minus I h bar d by dx, operating on psi, you know if you look for the eigenfunction equation, which is that, then you find solutions which form a complete set. They form these families of functions which can completely describe things, yes? I trust you're familiar with that sort of notion. If you have an Hermitian operator, if you solve that equation, you get a family of wave functions, like all the sinusoids, or in the case of our slit, all these slits, which can then be used to describe any wave function. So, that's why we end up talking about Hermitian operators. Okay. Now, it's very interesting that the world we live in is hierarchical, that you have different scales. You've got the quantum scale, which we don't see, so we can describe the world in terms of quantum of classical mechanics. And we have the thermodynamic scale, you know, all these tiny things and bits. The world's sort of hierarchical. Because it's hierarchical, it means we can understand it. Whereas imagine if all the scales were the same, it'd be a lot more messy. It's very interesting, that's the way it comes out. And the reason why it has this hierarchy is because of the different length scales of forces. So astronomy is governed by gravity, so it's on a very big scale. What we see here is governed by electrostatics, so it's on this scale. And nuclear forces are governed by nuclear forces on a much shorter scale. And so it's this scale that does things properly. Right, okay, so let's now start to say, okay, let's now try and start looking at the world with this knowledge. So our starting point is that the motion of things is governed by a wave function, and the wave function is linear, and a measurement consists in working out components of this wave, and the probability of it having one of those is given by the amplitude of the waves. And that is a version of the postulates of quantum mechanics. So we have a wave function, it's linear, you can decompose it, and the square of the coefficients give the probabilities. So let's just start from that and see where it gets us. Now, okay. So, what we haven't got in that description is something which tells us how the wave varies with time. Actually, what we haven't got is something which tells us how the wave varies with time. So you propose you've got a wave function. We have no idea what it is. We have no idea what it refers to. We just know that we've got a wave function, right? Yeah? We know we can split it up. But more than that, we have absolutely no idea what it is. Okay? Except you must be able to express it in terms of coordinates, like position and time, yes? But what it is and to what it refers, we have no idea. Now, what we're interested in, if you want to do physics, is how it changes with time. So what you want is to get d psi dt. Because if you know that, then you can see how it changes with time, and you can actually do physics, do you see? So having got this wave function, what you really want is something which tells you how it changes with time. You can say, well, supposing there is an operator which lets us do that. Supposing you can take the state of a wave function, you do something to it, and you get this. Supposing you can do that trick. Now again, that's a sort of hope. It's an aspiration, but not an unreasonable one. You see, we don't see memory effects in nature. You know, what happens depends on the state of things now, not what it was like 10 minutes ago, yes? So it's quite reasonable that we might be able to find something which says if you look at the state of the system now, you can work out how it will change, do you see? Yes, that's not an unreasonable thing to suppose. So there's this t operator, something which takes the wave function we've got now and works out how it's going to change. Now, what would have to be true about this t operator? Now, supposing our system is isolated. If our system is isolated, so we don't know what this t operator is, we have no idea what the t operator is, but let's just think about what some of its properties must be. Now, if you have an isolated system, then you have a clock. Now, because it's isolated, if you change the time on the clock, it doesn't change what happens, does it? Yes? You set the clock to read a certain thing, and you write what happens in terms of position and time. Now you can arbitrarily say, okay, right, I just want to change that by 10 seconds. We'll arbitrarily change the reading on the clock by 10 seconds. It doesn't make a blind bit of difference, does it? Yes? That means this, whatever this t operator is, it must not explicitly contain t. Otherwise, when you change the time on the clock, it changes. So there's no t in the t operator. The other thing we know, or at least we hope to goodness, is the t operator doesn't have things like d by dt in it, because the whole point of this thing is to find it. So we can therefore conclude, quite reasonably, that this t operator is a function of spatial coordinates only. Right? So the thing which tells us how, for an isolated system, what we're hoping to find, and indeed is only of any use if we do find something, and there's every reason to expect there is something, because what happens is it propagates in a certain way. It is therefore reasonable to expect you can find some function of the coordinates of the system which tell you how it will change with time. Okay, let's then proceed. Now, this is then an equation which we want to solve. But we can't solve it properly because we haven't got the foggiest idea what t is, except that it has nothing to do with time. Right? Because we want to get, and it's going to give us how the wave function, but we know nothing about it, except it doesn't contain t. Okay, but what we can do is use the standard trick. Let's suppose the wave function separates. Now, R is not just x, y, and z, but it's whatever you need. Whatever spatial coordinates you need. We have no idea what's in this system. We have no idea what it's composed of. But there will be spatial coordinates in there, right? So it doesn't mean just one particle. It could be a million particles. We have no idea what they are. It's something to do with spatial coordinates. And then we have time. Now we can propose that it would separate. Now because this t function has absolutely nothing to do with time coordinates, the separation works. So t operating on these two will give us t operating on the side if we're looking for spatial separable things, and the equation separates. Which means whatever this t operator is, acting on this divided by the spatial bit, gives you this. Now this bit we don't know what to do with, but that bit we can solve. because this is standard separation of variables, that must be a constant, and we end up with saying it's a constant, and therefore the time has to be of this form. It has to be exponentially decaying. Now, fine. But then you say, well, look, this is a fat lot of grid, because this operator, d by dt is not Hermitian. So we have found functions, but they're not going to be one of these nice sets. They're not complete sets. So we can't use these functions we've just found. If we found the spatial functions which were the solution of that, we couldn't use them, because they wouldn't form a complete set. So they're useless. But you realise that if instead you start off by putting an I in front of it, that is a Hermitian operator. So if you do exactly the same thing, exactly the same maths, it's just you say, okay, I'll scale this, my t operator, which will for some reason we'll call h, acting on psi gives us I times that. Of course, you can do that quite legitimately, because if you've got an operator which gives you d by dt, you multiply it by I, and you get one that gets you d by dt times I, yes? So you input the I in, because then when you redo that, you get separation of variables. These wave functions will now be a complete set, and they must have that time dependence. So we've deduced that from the basic observations, which is there's a wave function, and that is linear, we've deduced that you can write it in terms of things like that. Right? And the time dependence, you can write it as a sum of functions like that. Okay. Now let's then think, so we can write it like that, okay. Now, let's now work out, have you done this bracket notation in quantum yet? Yes, so it's just a way of doing the integrals, yes? So you can do that integral, and you've got the wave functions in it, and of course the wave functions are mutually orthogonal, because they are this complete basis set, which means then you end up with this. So what it means is, if you then look for the average value of omega, averaged over all of these things, it's this, and this is a constant, because these are the constant coefficients. So what we've done is shown that you can set up a t operator, multiply by I to make it Hermitian. If you then work out what its average value of its eigenvalue is, it's constant. And that is what energy is, and that is why it's conserved. That is what energy is. Now, when you do classical mechanics, energy enters in various ways. We measure forces, we invent energy to make life easy. We discover that it's conserved, etc., etc. But all the time we're asking, does its energy exist? What is it? Where does it come from? And that is what energy is, and that is where it comes from. Basically, what's happened, you see, is that you've shown you can write the wave function in a form of a linear combination of things which are separated. And if you then look arbitrarily, because it takes you fancy, and what the expectation value of this thing is, it turns out is constant and doesn't change. So there is this constant, which is a constant of the motion, and that's where it comes from. And of course, this then becomes our energy. Now, okay, fine. Now that means, therefore, that we are looking for a function h, which gives the time dependence. So what we've deduced is then there is some function of spatial coordinates for an isolated system. There is some function. We don't yet have any idea what it is. It's a function of spatial coordinates. We have no idea what the spatial coordinates are, to what they refer, or anything. But whatever it is, it gives the property, h bar is arbitrary, call it what you like, so we call it h bar of that. Okay, and of course we've basically derived the last postulate of quantum mechanics, that the time dependence is given by an operator. Okay, at this stage we don't know what the operator is, but we've basically derived that postulate from the other ones. It just follows from the fact that waves are linear. If the waves are linear, then that has to inform the time dependence when the h is a function of time and the expectation value of h is constant. It just follows from the waves being linear. That's all it takes. Now, let's just try say, okay, suppose we have an isolated system. What we could do is we could describe all the coordinates of the system in terms of a reference point. So you have your isolated system, and you assign within the system a reference point. So now you have proper three coordinates, x, y, and z, which are the reference point in your system from which all the other coordinates, whatever they are, and to whatever they refer, are defined. Now, if furthermore, so that means then that if you then say, right, the way that because this system is isolated, yes, what it does doesn't depend on where you draw the origin. So I put the origin there, or I put the origin there, and it doesn't make a blind bit of difference to anything. Right? That means how this varies with time doesn't depend on where you put it. Yes? That means the Hamiltonian doesn't depend on it. The H doesn't depend on it. That means the wave function will separate. It'll separate into a bit, which is going to be our centre of mass coordinates, and the rest. Okay? And it has to, just because it's an isolated system. So all of a sudden, we're seeing how you can describe a complex system in terms of the centre of mass notion. And we begin to understand why a molecule is going to diffract on the centre of mass, because this is just something you can do. And that means, therefore, you can then say, well, supposing there's H naught is whatever might apply that's left over to where it lies, and this then is our centre of mass Hamiltonian. Now, fine, you then deduce that the external one, Hamiltonian, that acts on the whole caboodle, must be written in terms of, you have to take off the internal energies. Fair enough. Then it's just the energy to the external motion. Right, so far what we've got, we found what energy is, we found that it's conserved, and we realise you can think about this thing in terms of central mass coordinates and the rest. Now, let's now think about, and we have one operator that we know, d by dt, well, that's obvious because that's what we're looking for. We have a Hamiltonian and we've got the foggiest about. Now let's apply relativity to this. Now let's look at the whole thing from a different frame of reference. So we basically have the standard transformation, which means then our wave function. Now the internal coordinates are still internal coordinates, and we won't worry about how they transform, they just transform something. But the external coordinates, we know how they transform, so you put those in. And you then say, okay, now let's do d by dt prime. Let's work out how this thing will change in the new frame of reference. But we have our wave function now written, the external bit, in terms of the external behaviour. But the point is that now there's t dependence in this thing, which is arrived because this wave function, which used to be purely spatial, the coordinates have been transformed to a purely spatial coordinate, then has t in it. Therefore, if you wish to know d by dt of this, you have to work out what d by dx is and use the chain rule. Yeah? So, when you change coordinate system, what was just worked out in dependency of d by dt, you start needing d by dx as well. Yes? Because what was a pure, if you do d by dt on something which is a function of x, y, and z, that's fine. But if you replace x with x prime minus bt prime, and now do d by dt prime, you look at how fast it changes in the new frame of reference, all of a sudden this spatial bit starts to have a time dependence. So if you want to know the time dependence, you have to worry about how fast this bit varies in space. So all of a sudden, you realise that when you go to a different frame of reference, if you wish to know how, you see, we started in one frame of reference. We wanted something which tells us how fast does the wave function change in this frame of reference. We got the answer. Then you say, that's fine. But now I want to work out how fast it changes when I look at it from a different frame of reference. But it turns out, in order to work out that out, you need to know the original how fast it changed, but you also need to know d by dx as well. So when you look at a different frame, you start getting d by dx's in. Now, if you then follow the maths through, you realise that these operators then are transformed like Lorentz coordinates, basically. And so that suggests, you know, instead of x, instead of t, you have that one. Instead you have these px, we call them px for obvious reasons, that means d by dx. You find that in one frame of reference, you get away with just a d by dt. If you want to know what d by dt is in another frame of reference, you also need to know d by dx in the first. And so to get the new d by dt in the new frame of reference, you need that as well. This suggests it might be convenient to put the whole thing together into a 4 vector. Now, at this point, we haven't actually, okay. Now, in relativity, you have 4 vectors. Their expectation values are frame independent, right? Okay, so let's do that. Let's work out the expectation of this thing value in frame independent. And what you find is that the energy in your initial frame of reference is given by the energy in your new frame of reference minus the expectation values of this d by dx operator times c squared. And you show that the energy in one frame transforms to the energy minus p squared in another. All right? Now, fine, that's what you've shown. So you start off by doing d by dt in 1. You change frame of reference, and the d by dt becomes a mixture of d by dt and d by dx. Because when you change, you start off with just d by dt in one frame of reference. You want, in the initial frame of reference, we want to know how fast it changes with time. We start off worrying about what's d by dt of our wave function. And we set that up. We had h as equal to that. But then we said, okay, but now I want to know how fast the wave function changes when I look in a different frame of reference. But because these spatial bits, in terms of x, y, and z, the x becomes direct transform and suddenly has a t in it. So if you want to get that, you also have to worry, in a different frame of reference, about deciding x. Yeah? And the rule that connects them, these are the rule that connects the expectation values of them. Now you've seen that expression before. Yes? And that is this one. Yeah? So what we've done is we've shown you take the basic observation of quantum mechanics, that they are waves and they are linear. And that averages are given by the square of the coefficients. You then, without knowing what the wave function is, what coordinates you need, just propose that we seek for something which tells us how it changes with time. And you work out that this is constant, the expectation value is this thing is constant in your initial frame of reference. You then change frame of reference, and you discover that because the x and t's get muddled up, the d by dt gets muddled up by d by dx. And so in the new frame of reference, to work out the same quantity, you need something that comes from d by dt and something that comes from d by dx. You then look at your classical expressions, relativity, and say, aha, well, I've done enough quantum mechanics to know that d by dx relates to p, so we'll call it p. But the shock is you've derived this, and it should be that. And that therefore proves that E equals mc squared, and shows you why E equals mc squared. The n is just the energy in the stationary frame of reference. And we deduced that to work out what energy is. Energy is the expectation value of the T operator. We gaily and merrily worked out it was conserved. We then changed frame of reference and worked out that if you would need to know the energy in a different frame of reference, you need to offset it by something. And if you do, this is a rinse and invariant, and you get back what you had fast. Fine. But the shock is that, so this is something that's constant in the motion. It's the energy in the centre of mass frame. Well, energy in the zero momentum frame, it turns out. Not centre of mass, in zero momentum frame. But then you compare it with classical mechanics, and you realise then that this thing must be what we've hit on, and we call mass. So that shows, you see, that mass is nothing more or less than energy stored in internal degrees of freedom or whatever you've got. Which is why E equals mc squared. And it just follows from the fact they're linear waves. Now, can you see what people are trying to do with physics? You see, the name of the game with physics is you want to try and do this sort of trick on the whole thing. To start off by saying, what's space like? What's its behaviour? How does it work? Now, this is what the standard model of physics does, and it's got a fair way along it. And so you find, for example, that basically each field has different properties. And you could say, well, look, if I had a field, you could have this symmetry property, which gets you the Higgs field. Or you could have this property, get the electrostatic field. Or you could have this symmetry property, and you get the gravitational field. And so the different fields you get are the ones that would be permitted by the symmetry of what a field could be like, basically. And so you can start by saying, well, and so all of a sudden, you see that the whole thing is set according to what's required by the symmetry of space. And what you can mathematically, what you can do to a wave function determines the sorts of stuff you get. And the whole point of this grand unified theory stuff is trying to work out, keep pushing down and down and down, till you work out if you can see a connection between them. Now, there's general recognition, I think, that quantum mechanics has got into a hole, and we're not getting any further with it. And there are myriads of different interpretations of quantum mechanics. A colleague of mine maintains there are 14 different interpretations of quantum mechanics. Things that people have written extensively on as a way, other than the Copenhagen one. And the astonishing thing is all 14 give the same results, which they better have, because they're all trying to describe the world as we see it. And so the actual quantum mechanics we've got is completely robust. And the problem is it completely explains everything we can see. Right? And so unless someone can measure something which sheds light on it, then we're not going to get anywhere. So we need some more measurements, basically. And there are obviously very interesting measurements like entanglement, which cause serious problems, which I may talk about in a minute if we've got time. But fundamentally, we need more measurements. But the other thing I think is a general perception is that we're looking at it from the wrong angle, basically. That somehow we've got ourselves boxed into a way of looking at it, which is looking at it from the wrong perspective. And I hope this procedure illustrates what is meant by that notion. Because if you just look at everything you've learned from a different angle, saying, okay, let's just start from the experimental observations of wave and see where it gets us, we just derive the whole of classical relativistic mechanics pretty much on that basis. You see, looking from a different perspective brings results. And this is what is needed. The problem is you have to look at it from a different perspective, which is part of the challenge of quantum mechanics. Okay. But I hope that's showing this. It shows you the name of the game, what needs to be done, and what sort of things people are doing. Now, let's just do something else. Let's just think, that's the Schrödinger equation. Where might that come from? Well, historically what happened was that Schrödinger knew about the Lorentz and he knew about this. E squared equals P squared, C squared plus M squared, C to the fourth. He knew that. And I think he knew enough to work out that the energy related to the time operator. So he tried the equation, which is minus h bar squared d2 psi dt squared equals minus h bar squared 2m minus h bar squared, that term, sorry, minus h bar squared d2 psi dx squared, or del squared psi, plus m squared c squared psi. So that was the first equation he actually tried. And what he did is he translated Einstein's energy momentum invariant into operators. This is just a guess. And that's the first thing he guessed. And it's called the Klein-Gordon equation. And indeed, it is accepted as being a perfect, well, good under some circumstances, equation of relativistic quantum mechanics. Schrödinger then tried to use it and discovered it was a complete pain in the neck, not least because it had that squared in it. Yes? So he gave up and started working at the non-relativistic case, and he came up with this famous equation. So that's actually what happened. So we've got this thing called the Klein-Gordon equation. Now, what we have, you see, is this operator, which is that. And if we work out its length, it's that times itself, which is this thing squared, which looks like that. And can you see that this is just Klein-Gordon's, the operator of that? So if we then operate that on the wave function and integrate over the internal degrees of freedom, which I'm not quite sure how you do, but hence it myself, you end up with the Klein-Gordon equation. So the scheme we've got gives a justification for sort of a priori for this equation, which Schrödinger called us a thin n, because we've derived the h and the p, as it were, from the d by dt and d from scratch. But let's look at this thing. So what we've got is that your d by dt squared, you can take the m squared c squared out as a common factor, and you end up with this thing. Now, what we actually want, is the square root of this. Now, you could write this thing as binomial expansion, and it works with operators, which would mean you get the square root of that is IH bar d by dt. There's a plus and minus in this. That would be plus or minus this lot, and that then is the term of the Schrödinger equation. So if you take this thing and do a low velocity, a low momentum expansion on it, you end up with the kinetic energy part of the Schrödinger equation, basically. So that's where the Schrödinger equation comes from. So I don't expect you to see the details. What I'm trying to illustrate is that, again, even the Schrödinger equation itself, at heart, follows from all this stuff. Okay. So now let's just finish briefly. Let's go back and think a bit about measurement. Because the thing that's not really not understood about quantum mechanics is what happens when you measure. And you have all sorts of attempts to explain it, not least this many worlds hypothesis, which strikes me as, well, I think you have to have a lobotomy before you can believe that. So every time something happens, there are many, many parts, yes? And so each nanosecond, it bifurcates into a very large number of things, right? And so you end up with 10 to the goodness knows how many after 1 microsecond, and then you multiply that by that in the next microsecond, so you double that, and that, and that, and that, and that. Just how many of these things you're proposing to have. And the reason is because we don't understand measurement, we don't understand how the probability could thing. So rather than accept the thing behaves in a probabilistic fashion, and maybe we should be looking as to why that happens, people just say, well, it's not probabilistic, we just didn't see one route. It seems to me to have really given up on trying to understand what's going on. And quite interesting is why people take such pleasure in burying their heads in the sand and going for a theory like that, which basically says we don't want to think about it. So let's think about what happens. The first thing is this. So you have some sort of aperture. You've done this in waves, yes? And the wave comes along, and you end up with a fraction pattern over here. Fine, that's fine. But supposing you put a grain of something like silver iodide, if the part of the wave gets to here, it carries on. If it gets to here, it stops. And with a certain probability, it can change the crystal color. Right? Now, the first thing we have deduced is that the wave is everywhere. It's not, the wave itself is not located. But the point is, it can propagate through holes, in which case the whole wave just carries on propagating. But if you put something in the way which eats it, then it will be eaten according to the probability, the probability that it strikes it. Right? And that's the basic observation, which is very strange. So how could this be? Well, supposing you have a violin string, and if you hit it at the right place, you will excite, for example, this normal mode. Okay, you'll excite the others as well, but you will excite that particular normal mode, amongst others. Now, can you see that if you hit the violin string there, or there, or there, or there, whilst the proportion of the other modes will change, the chance of exciting that one will be the same. Now, you can do this in quantum mechanics. You can take a quantum chain, you can take some masses with springs between them, and you can do it as quantum mechanics. It's called, this is simple harmonic motion, but just done for a more complicated system. So it's like simple harmonic motion in quantum mechanics. You do this next term in solid-state physics, and the vibration is called photons. And so you end up with quantized versions. So instead of the simple harmonic oscillator has one particle going to and fro, this has all the particles in some normal mode, right? Now, it is also true with this, that if you hit it here, you can excite the mode with equal chance of hitting it at the different places, right? But the thing which is excited is a mode which covers the whole of the chain. Now, quantum mechanically, what you could do is you could do it in reverse. What you could do is you could have located here, you could have a potential system like this, where you have, say, an electron located in a potential well, the barrier high enough so the rate of tunneling through it is not very significant. So you can put detectors next to each atom. Right? And you could add a coupling in the Hamiltonian between the two. And what will happen, you see, is that, and this simulates a measurement, because this is like a silver iodide crystal. There's an electron in this particular state, when it's kicked, it jumps out, it goes running off at high speed, hits other thing, and causes the whole crystal to go black. So it's a pretty good model of a silver iodide crystal. Now, if you hit it here, you generate the mode. If you hit it there, you generate the same mode. If you hit it there, you generate the same mode. In physics, what goes up can also come down. That means, therefore, if you have this thing, and have it linked to all these things, it can excite each one of these with equal probability. Yes? So if it excites this one, you deduce the phonon was here. If it excites that one, you deduce it was here. If it excites that one, you deduce it was here. But it wasn't in any of them. It was actually everywhere. And so when your wave comes to your piece of photographic film, it's not located in one place. It's everywhere. But you have different detectors. And the one that fires, you say it was there. Do you see? And so the problem is, what causes these detectors to randomly fire? That's the heart of it. Now, if you just, this is a system you can actually encode quite simply and work out what happens. Now, if you just do it as simply as that and run the system through, what you find, of course, is that each of these fires together with some probability. But that's not what happens in real life. Now, the question then is why in real life does it choose one of them? Now, have you ever seen the couple pendulum? I hope to bring them. Two pendulum bobs like this, and they're out of phase with each other. Did they show this in mechanics? And the energy transfers from one to the other. So if you have an oscillating system in phase behind another one, it can transfer all its energy to that one. Yes? So supposing these detectors were oscillating systems, each will have a different phase relationship to this. These, some of them will be ahead of this, some of these will be behind. Can you see that what could happen is that just like with those two bobs, the energy gets sucked into the one that's ahead. You can imagine some scheme where what happens is the energy gets transferred into the one which has the right phase relationship. And you have something like, it's the random phase relationship of these compared to your system, which determines which one fires. So there are mechanisms which could be explored, which would explain why, but that is something which that's not been done, but you can see the sort of problems that one might like to worry about. One last thing I would say is that there's further evidence of these waves being flipped in space and large. For example, there's a colleague of mine who did laser spectroscopy. The wave packet lengths he deals with equals the distance between here and the moon. So his photon is spread over that length. The waves can be very big, and that's an experimental fact. And so to take this experiment, you have an atom, it emits two photons. This one is circularly polarized, and this one is circularly polarized. By conservation energy, they're actually the same. So you measure the circular polarization here of this one, and over here, which is a long way away, you find that whatever you measure here, the one that comes over here has the opposite polarization. The problem is, this is so far away from that, there's no way that the signal could have got from that to this. Plus also causality dictates that if in one frame of reference that happens first and that second, you go at a certain speed, that happens first and that second. Right? So people spend lots of time thinking about this, but the one thing we're not facing up to the fact is we're just not facing up to the fact that what you measure here does not cause what you measure here. And that's obvious, it can't, because it happens too fast. That means what happens here and here is predetermined. But they've shown that there are no hidden variables, as you can show that experimentally, but there are local hidden variables. And if you had something which extended through space against which these things could compare themselves, then that might explain it. And there are things which extend through space. The space is called a zero-point motion, with things fluctuating, etc., etc. But again, we're not making progress with this because people are totally hung up on this entanglement experiment. Because the blindingly obvious fact is that what happens here is not caused by what happens here. That means it's predetermined. And again, people run a million miles from this. So they don't wish it to be predetermined. So don't quantum mechanics. It's quite nice if things are undetermined. That suits us just fine. But the point is, actually, it is the natural assumption, conclusion of that is predetermined. But anyway, that's another story. Thank you for your attention.